So today we're going to be doing May-June 2022 paper 41. Question number 1 says, the solubility of the group 2 sulfates decreases down the group. Explain this trend. Now the solubility can be explained by the enthalpy change of solution, right? So down the group what happens is that the enthalpy change of solution, okay, delta H solution becomes more endothermic, okay, becomes more endothermic. The reason why is because as we go down the group, right, the lattice enthalpy and the hydration enthalpy both become less exothermic. Lattice enthalpy and hydration enthalpy both become less exothermic. However, the enthalpy of hydration changes by a greater amount, okay? However, the enthalpy of hydration, okay, enthalpy change of hydration, delta H hydration changes by a greater amount. By a greater amount. Again, the more exothermic lattice enthalpy, the more favorable the solid formation is. The more exothermic the hydration enthalpy, the more favorable the aqueous ions are. Down the group, if enthalpy of solution is becoming more endothermic, that means the solubility is decreasing. The solubility is decreasing means that aqueous ion formation is less favored. Aqueous ion formation is less favored means that the enthalpy change of hydration is not as exothermic because it's changing by a greater amount. Okay. Describe what is observed when magnesium and barium are reacted separately with an excess of dilute sulfuric acid. Now, when magnesium reacts with dilute sulfuric acid, we get magnesium sulfate and hydrogen gas. Okay, but in the case of magnesium sulfate, right, it's soluble. We're not going to see a precipitate form. Okay, all we're going to see is effervescence or fizzing of hydrogen gas. Okay, we're going to see effervescence, and the metal will dissolve. Right, the metal will dissolve. Okay, with barium, what we're going to see is we're going to see the formation of a white precipitate, right? That's barium sulfate forming. The white precipitate forms. Okay, we're also going to see effervescence. Okay, and then we're also going to see the metal disappear. Okay, plus the metal dissolves. The Ksp of barium sulfate is 1.08 into 10 to the power minus 10 moles squared per dm to the power 6 or dm to the power minus 6 at 298 Kelvin. Calculate the solubility of barium sulfate in grams per 100 cm cube of solution. So we're going to talk about the units at the end. Okay, first we just need to find the solubility in moles per dm cube. So what we have here is we have barium sulfate, right, partially soluble. You get barium ions and sulfate ions. Now let's say that the solubility of barium sulfate is x moles per dm cube. So let's say x moles per dm cube dissolve of barium sulfate. That means we have x moles per dm cube of barium ions and x moles per dm cube of sulfate ions. Again, the solubility is simply the concentration of a saturated solution. So all we're saying is we want to find how much barium sulfate would dissolve per decimeter cube. So we call that x. So x mole per dm cube dissolve. And we have x moles per dm cube of barium and x moles per dm cube of sulfate. The Ksp for this is the concentration of barium times the concentration of sulfate. The concentration of barium over here is x, the concentration of sulfate is x, and the Ksp is 1.08 into 10 to the power minus 10. If we take the square root, we get x is equal to 1.04 into 10 to the power of minus 5 moles per decimeter cube. So that's the solubility in moles per decimeter cube. We want to convert to grams per 100 centimeter cube. So the first thing we do is if you want to go from moles per decimeter cube, to grams per decimeter cube, all you have to do is multiply by the MR. Okay, you want to go from moles to mass. So we multiply by the molar mass. So here, if we multiply 1.04 into 10 to the power of minus 5 with the MR, which is 233.4, 2.43 into 10 to the power of negative 3 grams per decimeter cube. So now we have the concentration in grams per decimeter cube of a saturated solution. We want to know how much dissolves in 100 cm cube. So if we have 2.43 into 10 to the power minus 3 grams dissolving in 1000 cm cube, right? In 100 cm cube, we're going to have 1/10 the amount, right? In a 100 cm cube, we're going to have 1/10 the amount. So we just divide this value by 10 and we get 2.43 into 10 to the power of -4. The equation for the formation of a gaseous sulfate ion is shown. Calculate the standard enthalpy change of formation of sulfate ions. It may be helpful to draw a labeled energy cycle. Use relevant data from table 1.1 in your calculations. Now over here, we don't need to draw a full Born-Haber cycle. Okay, we just want to find the enthalpy change of formation of sulfate ions. We want to find the enthalpy change of formation of these gaseous sulfate ions, right? So what we can do here is we can start off by trying to make a Hess cycle. Okay, we want to make a Hess cycle or an energy cycle. We can say, okay, I want to find the enthalpy change of formation of sulfate ions. So I'm going to start with the elements. Okay, I'm going to start with the elements here, right? I want to find the enthalpy change of formation of sulfate ions. So here I have SO4 2 minus gaseous, right? Now, what other values do we have that relate to gaseous ions, Well, we want to go from elements to gaseous ions, right? So that's the enthalpy change of formation of sulfate, right? The gaseous sulfate ions, that's what we want to find, okay? Here we have gaseous ions, so let me write down the other gaseous ion that we have. We're talking about barium sulfate here, right? The data given to us is for barium sulfate, and then obviously the sulfur and the oxygens, right? So the other gaseous ions that we're talking about is the barium ion, right? So these are the two gaseous ions that make up, barium sulfate, and we're also given the lattice enthalpy. Right? The lattice enthalpy is the enthalpy change when 1 mole of barium sulfate, is formed from the gaseous ions. So I can say, okay, I can write barium sulfate solid here. The reason I'm writing barium sulfate solid here is because we have the enthalpy change of formation of barium sulfate. That's the enthalpy change when 1 mole of barium sulfate is made from the elements. We also have the lattice enthalpy of barium sulfate. That's when 1 mole of barium sulfate is made from the gaseous ions. So the way to complete this energy cycle is by saying, okay, first I have gaseous ions here, so let me write those down. I want to find the formation of gaseous sulfate ions. So I know that we're talking about making sulfate ions from the elements. Then we know that, okay, the data given to us means that the other gaseous ion that we're looking at here is the barium ion. So let's write the gaseous ions together. Then we're saying, okay, how do I complete the cycle? What enthalpy changes are given to us that we can use to find the enthalpy change of formation of the gaseous sulfate ion? How do we complete the cycle? Well, we have the formation of barium sulfate and the lattice enthalpy of barium sulfate. So we know that solid barium sulfate, elements to barium sulfate is formation. Elements to barium sulfate is formation of barium sulfate. That is given to us in -1473. And we have the lattice enthalpy, that's gaseous ions to solid lattice, that is -2469. And now the only thing missing here is the formation of gaseous barium ions from the element. Right? So here what are we doing? We're starting with the elemental barium, that's barium solid. So first we're going to atomize it, right? We have 1 mole of barium atoms. Here. So atomization, that's atomization of barium, plus the first plus the second ionization energy, right? We're going from barium atoms, solid atoms, to gaseous atoms, and then we're going from gaseous atoms to 2 plus gaseous ions. So we have atomization plus the first ionization energy plus the second ionization energy, and that is equal to the atomization is given to us here, 180. First ionization is 503 plus 965. So 180 plus 503 plus 965. So now if we look at our energy cycle, we can find the enthalpy change of formation of gaseous sulfate ions. All the arrows are going away from the elements, right? And then all the arrows eventually point towards solid barium sulfate, right? All the arrows are pointing towards barium sulfate. All the arrows are leaving from the elements. So we're saying that we can go from elements to gaseous ions, and then gaseous ions to solid lattice, and that is equal to going directly from elements to the solid lattice. So we can say here that the equation that we get is the enthalpy change of formation of the gaseous sulfate ions plus 180 plus 503 plus 965, 180 plus 503 plus 965 plus the lattice enthalpy, that's minus 2469 is equal to minus 1473. That's equal to minus 1473. Okay, again we're saying this plus this is equal to this. And then that gives us the formation of sulfate as, that gives us the enthalpy change of formation of sulfate ions as negative 652 kilojoules per mole. Negative 652 kilojoules per mole. Suggest how the lattice energy of barium sulfate differs from the lattice energy of cesium sulfate. Cesium over here is in group 1. Okay, it comes just before barium. It comes just before barium. So over here, cesium obviously has a 1 plus charge, right? Cesium has a 1 plus charge. Okay, same period as barium, right? Same period as barium. So that means that it has a larger size and a smaller charge, which means it has weaker ionic bonds, right? Weaker ionic bonds. Again, the greater the charge, right? Barium ions have a greater charge. They have a greater charge and they're across the period, so they have a smaller radius. Greater charge, smaller radius means more exothermic lattice enthalpy. So we can say that the lattice energy for barium sulfate is more exothermic, because the barium ion, okay, has a greater charge, and smaller radius, okay, or you can say greater charge density, than the cesium ion. Therefore, the electrostatic forces of attraction, that's the ionic bonds, right, between barium and sulfate ions are stronger, okay, are stronger in barium sulfate than they are between cesium and sulfate ions in cesium sulfate, okay. The reaction of solid hydrated barium hydroxide with ammonium salts is endothermic. Calculate the minimum temperature at which the reaction of hydrated barium hydroxide with ammonium nitrate becomes feasible. Show all your working. The temperature at which it becomes feasible means that the delta G is equal to 0, right? And we know that the Gibbs free energy change is delta G is equal to delta H minus T delta S. So here delta H is positive 132. So we have 132 for delta H minus the temperature. We don't know that. The entropy change is 616 joules per Kelvin per mole. We have 616 divided by 1000, which is just 0.616, is 0.616, and this is equal to 0. Okay, we said delta G is equal to 0. Delta H minus T delta S is equal to 0. You rearrange, you get 0.616 T is equal to 132, which gives us the temperature as 214.3 Kelvin. We want to find the temperature in degrees Celsius, so we can just take the temperature and subtract 273. So it's degrees Celsius, that will be 214.3 minus 273. That gives us negative 58.7 degrees Celsius. Negative 58.7 degrees Celsius. Barium hydroxide reacts readily with ammonium chloride on mixing at room temperature. Some relevant standard entropies are given in table 1.2. Calculate the standard Gibbs free energy change for this reaction at 25 degrees Celsius. So now in this case, the enthalpy change is given to us. We have to first find the entropy change and then delta G. So the entropy change here, delta S, is the entropy of products minus the entropy of the reactants. The products over here are the hydrated barium chloride, ammonia, and H2O. So we have hydrated barium chloride, which is 203. We have 1 mole of that, 203, plus 8 moles of water, so 8 times 70. We have 2 moles of ammonia, so that would be 2 times 192. And then we subtract the reactants. We have 2 moles of ammonium chloride, so that would be minus 2 times 95. And then we have 1 mole of this hydrated barium hydroxide, that will be minus 427. That gives us the entropy change as plus 530 joules per Kelvin per mole. Okay. Now we want to find delta G. Delta G is equal to delta H minus T delta S. Delta H is given to us as 133. 133. We want to find the standard Gibbs free energy change at 25 degrees Celsius. The temperature is 298 Kelvin. Delta S is 530 joules per Kelvin per mole. Again, we want to convert this to kilojoules, so divide by 1000. So you get 0.530 kilojoules per Kelvin per mole. And that gives us delta G as negative 24.9 kilojoules per mole. Negative 24.9 kilojoules per mole. So that's our answer. Here we have question number 2, which says define transition element. A transition element is an element that has at least one stable ion, with a partially filled D subshell. With a partially filled D subshell or partially filled D orbitals. Okay, partially filled D subshell. Sketch the shape of a 3D Z squared orbital. The 3D Z squared orbital is going to be along the Z axis. Okay, so we're going to have this lobe similar to what we have with a p orbital, right? This double lobe, and then we have this sort of donut shape around the origin. Okay, we have this sort of donut shape around these two lobes. Okay, this dumbbell shape. Magnesium oxide acts as a heterogeneous catalyst in the decomposition of hydrogen peroxide. Explain what is meant by a heterogeneous catalyst. A heterogeneous catalyst is a catalyst in a different physical state than the reactants. Okay, in a different physical state than the reactants, or different physical phase than the reactants. They can ask for a longer explanation here. Okay, if it's for more marks, they would give you more space, in which case you would first define what a catalyst is and then say that it's in a different physical state. So if I asked you for a longer explanation, you would say a reagent that increases the rate of a chemical reaction by providing an alternative mechanism with a lower activation energy, and it is in a different physical state than the reactant. So explain what a catalyst is and then explain what a heterogeneous catalyst is, or explain what is meant by heterogeneous. Describe the mode of action of a heterogeneous catalyst in a reaction. Heterogeneous catalysts work on the principle of adsorption. Adsorption, right? So what happens here is that the reactants diffuse to and adsorb, okay, adsorb or bond to the surface of the catalyst. And when these reactants bond to the surface of the catalyst, right, this results in the weakening of the bonds in the reactants. Okay, this results in the bonds becoming weaker. Okay, okay, in the reactants. And when the bonds become weaker, they're easier to break, right? That means we have a lower activation energy, thereby lowering the activation energy. As a result, the reaction occurs. Okay, the reaction occurs, and products form. Okay, and then the products desorb from the surface. Okay, desorb from the surface. Okay, so the bonds between the products and the surface of the catalyst break. Okay, desorption is the opposite. Okay, the bonds between the surface and the product break. Okay, from the surface. And now you have your final product. Manganese 7 oxide, Mn2O7, can be made by treatment of KMnO4 with a concentrated sulfuric acid. Mn2O7 readily decomposes at room temperature to form manganese 4 oxide and a colorless diatomic gas. Construct equations for both the reactions described. So in the first reaction, we have KMnO4 reacting with concentrated sulfuric acid to make Mn2O7. Mn2O7 can be made from KMnO4 and concentrated sulfuric acid. So here we have KMnO4 reacting with concentrated sulfuric acid to make Mn2O7. Mn2O7. We have to determine what the other products would be. So we have potassium and sulfate here. So we get potassium sulfate. We get potassium sulfate, that's K2SO4. And then these hydrogens, okay, will become part of H2O. So we get water. Now we have to balance this equation. We have 2 potassiums here. So we're going to write 2 KMnO4. We're going to write 2 KMnO4. Everything else is balanced. We have 2 manganese, right? We have 1 sulfate, we have 1 sulfate here, we have 2 hydrogens here, and then we have 2 times 4, 8 plus 4, 12 oxygens, and here we have 7 plus 4 plus 1, that's 12 oxygens. Everything else balances out. Aqueous manganese 2 ions show similar chemical properties to aqueous copper 2 ions when reacted separately with aqueous sodium hydroxide and with concentrated HCl. Write the ionic equation and state the type of reaction for the reaction of MnH2O6 2 plus with aqueous sodium hydroxide. So this is similar to the reaction with copper 2 hexaaqua, right? They're saying the manganese 2 ions react similarly to copper 2 ions. So what do we get here? We have MnH2O6 2 plus react with hydroxide ions, that's OH minus. For the ionic equation, we're going to have 2 OH minus here, and we end up getting a precipitate, right, of manganese hydroxide. Okay, so we get MnH2O4 and then OH twice, and then we have 2 H2O. This type of reaction is called a precipitation reaction. Right, the ionic equation state the type of reaction with the reaction of manganese 2 hexaaqua with concentrated HCl. Here we have a ligand exchange reaction. So we have MnH2O6 2 plus reacts with 4Cl minus, and we get MnCl4 2 minus. Again, this is what happens when we have copper 2 hexaaqua reacting with chloride, right? A similar reaction, and then we get 6 H2O. The reaction is called a ligand exchange reaction, or a ligand substitution reaction. Table 2.1 lists relevant electrode potential for some electrode reactions. Suggest the formula of the manganese species formed when Mn2 plus aqueous reacts with chlorine. Now, generally speaking, we know that chlorine is an oxidizing agent, right? Halogens are oxidizing agents, but halogens can also undergo disproportionation as shown here, right? So here they've shown chlorine losing electrons and undergoing oxidation. If you look at the backward reaction, chlorine is undergoing oxidation, but the electrode potential for the backward reaction is negative 1.64 volts, right? So that doesn't seem like a very feasible reaction. So we can ignore chlorine as a reducing agent or losing electrons. So here we're only thinking about chlorine undergoing reduction. Okay, it's going to be an oxidizing agent. Okay, it's going to be an oxidizing agent, undergoes reduction. So that will be the cathode, right? Because reduction occurs at the cathode, and then that means Mn2 plus will be undergoing oxidation. So again, we're going to ignore the first one, right? Because here Mn2 plus is undergoing reduction. Mn2 plus must be undergoing oxidation. Okay, so we're going to think about this equation as well as this equation, right? Now, we're first going to talk about this equation, right? Because Mn2 plus can form MnO2. Now, if this was the anode, right? We know that the cell or reaction potential is the electrode potential at the cathode minus the anode, right? Cathode minus anode, or reduction minus oxidation. Okay, reduction minus oxidation. So here, if chlorine is going to undergo reduction, that has an electrode potential of 1.36, and then at the anode we have positive 1.23, so we subtract that, so we get 0.13 volts. So we know that MnO2 will form. Okay, we know that MnO2 will form, but the question is, will this MnO2 be further oxidized to MnO4 minus? Will this MnO2 be further oxidized to MnO4 minus? But in this case, okay, what we have to think about is, again, we have the same oxidizing agent, that's chlorine, so that would be your cathode. That would be your cathode, that would be 1.36. And then we subtract the anode, in which case this would be the anode, the backward reaction here, right? So we're subtracting 1.67. And this gives us a reaction potential of minus 0.31 volts. So that means that this isn't feasible, right? The cell potential has to be greater than 0 for it to be feasible. That means that from Mn2 plus to MnO2 is feasible, but the second reaction with chlorine will not be feasible. Okay, so the final species is going to be MnO2. So the final species is going to be MnO2, and the type of reaction is a redox reaction. So here we have question number 3, which says the rate of reaction between 2-chloro-2-methylpropane and methanol is investigated. When a large excess of methanol is used, the overall reaction is first order. Okay, so we're using a large excess of methanol. So we can assume that the concentration of methanol is remaining constant because we have so much of methanol. A very small fraction of the methanol reacts. And therefore we can assume that the concentration isn't changing, and therefore it has no effect on the rate. So we can treat this as zero order with respect to methanol. And then we're saying that therefore it's first order with respect to the halogenoalkane, because the overall reaction is first order, and we just have this one reactant, right? Because we're ignoring methanol, so that means it must be first order with respect to the halogenoalkane. Figure 3.1 shows the results obtained. Use the graph to determine the rate of reaction at 40 seconds. Show all your working. So here we have a concentration time graph. We have a concentration versus time graph, right? And we know that the rate of the reaction is just a change in concentration over the change in time. In other words, we want to find the slope of the concentration time graph at 40 seconds. Okay. So over here, we draw the tangent at t is equal to 40 seconds. In order to determine this point on the x-axis, okay, you'll have to use a ruler, measure the width of the square, and then figure out how far away 40 would be from 25, right? So again, 40 is going to be 60% of the distance between 25 and 50. The difference between 50 and 25 is 25. The distance between 40 and 25 is 15. So 15 over 25 is 0.6. So again, you're going 60% of the distance. You're going 60% of the distance, or 60% of the width of the square from 25. So we draw this line, and then roughly speaking, I get here the x coordinate at 87. I get the x coordinate at 87. So I'm going to take this point as 87, 0, and then the y-intercept at 0.015, so that would be 0, 0.015. So the gradient over here comes out to y2 minus y1, so the 0.015 minus 0 divided by x2 minus x1, so 0 minus 87. So we get 0.015 minus 0 divided by 0 minus 87, So that gives you the slope as negative 1.72 into 10 to the power of minus 4. Now here the issue is that we're getting a negative slope. Why? Because we're looking at a reactant. The concentration of a reactant decreases with time, but the rate has to be given as a positive value. So we're going to take the absolute value of the slope. And that would give us the rate as positive 1.72 into 10 to the power of minus 4 moles per dm cube per second. Use the graph to show that the overall reaction is first order. Explain your answer. So to show that the reaction is overall first order, right, what we have to do is we have to look at successive half-lives, because we have a concentration time graph, right? We have only one reactant changing with time. So we can say the first half-life over here is going from 0.02 to 0.01, 0.02 to 0.01. This value comes out to roughly 30 seconds, okay, roughly 30 seconds. And then the second half-life, we're going from 0.01 to 0.005, 0.01 to 0.005. That value is roughly 60 seconds. So that value is roughly 60 seconds. So that means that the first half-life is from 0 to 30, the second half-life is from 30 to 60. So we're getting a half-life of 30 seconds. We have successive half-lives are constant, so therefore the reaction must be first order. So we can say successive half-lives are constant, right? I got a half-life as 30 seconds. Therefore, the reaction is first order, okay, with respect to the halogenoalkane. In a different reaction, which is also a first order reaction, 75% of the reactant is consumed in 320 seconds. Calculate the rate constant for this reaction. State the units for K. Now over here we know that the reaction is overall first order, right? We know that the reaction is overall first order, right? First order overall. And for such a reaction, the rate constant is equal to 0.693 divided by the half-life. 0.693 divided by the half-life. Now, we also know that initially, let's say I have 100% of the reactant. Let's say I have 100% of the reactant, okay? After one half-life, right, half the reactant would have reacted, so you have 50% left. You have 50% left. And then after a second half-life, you'd only have 25% left, right? Because half of that will react. So after the first half-life, half the reactants have reacted, so you're left with 50%. And then after the second half-life, half of the remaining amount has reacted, so you're left with 25%. So that means after two half-lives, 25% of the reactant is left. In other words, 75% of the reactant is consumed. 25% left means 75% of the reactant is consumed. So this happens in 320 seconds. So 2 times the half-life is 320 seconds. Okay, 2 times the half-life is 320 seconds, which gives us the half-life as 160 seconds. So we can say that K is 0.693 divided by the half-life, which is 160, and that gives us the value of K as 0.00433, and the units are just 1 over time. Okay, 1 over time, right? Because this is unitless. 0.693 divided by seconds. Okay, so we get per second for the units. We get per second for the units. Define standard electrode potential. Standard electrode potential is the voltage. It is the voltage of a half cell relative to the standard hydrogen electrode, relative to the standard hydrogen electrode at 298 Kelvin, 1 atmosphere of pressure, using 1 mole per dm cube solutions. Right, those are standard conditions for an electrochemical cell. A salt bridge is used in an electrochemical cell. State the function of the salt bridge. Explain your answer. So a salt bridge prevents, okay, it prevents the buildup of charge, right? It prevents the buildup of charge. It prevents the buildup of charge on either side, okay, on either half cell, and that completes the circuit. Okay, because it prevents the buildup of charge, okay, a salt bridge completes the circuit. How does it prevent the buildup of charge? Anions or negative ions can move from the salt bridge to the anode, okay, to prevent a buildup of excess positive charge, and cations can move from the salt bridge to the cathode to prevent the buildup of excess negative charge. Complete the diagram of the apparatus that can be used to measure the standard electrode potential of the dichromate 6H plus Cr3 plus electrode against the standard hydrogen electrode. The diagram should be fully labeled to identify all apparatus, substances, and conditions. So here we're going to use a platinum electrode for both of them because we have all ions over here, right? There's no metal in this equilibrium. And then the standard hydrogen electrode is ion and gas, right? We have an equilibrium between a gas and an ion. So we have platinum electrodes in both, right? Here I'm going to draw the standard hydrogen electrode like this. Okay, we have hydrogen gas at 298 Kelvin, okay, and 1 atmosphere of pressure. Okay, we have the wire that connects these two electrodes. We have a voltmeter in between. The salt bridge is already labeled for us. Okay, we label the voltmeter. And for the electrolytes here, right, we have 1 mole per dm cube H plus solution, and here we're going to have 1 mole per dm cube of each of these ions, right? 1 mole per dm cube Cr3 plus, we have 1 mole per dm cube of H plus, and we have 1 mole per dm cube of Cr2O7 2 minus. You should also write the state symbols, okay, for these. Write the state symbols, aqueous, and then this is also aqueous. And the last thing missing here is the platinum electrode. So we have platinum electrode here, and we have platinum electrode here. The standard reduction potential of the Cr2O7 2 minus H plus Cr3 plus aqueous electrode is positive 1.33 volts. Label the negative electrode and the direction of electron flow in the external circuit when the current flows in your diagram in C part 3. Now, the reduction potential for this is positive 1.33. For the standard hydrogen electrode, the reduction potential is 0.00 volts, right? And that's for this particular equilibrium, right? 2H plus plus 2E gives you hydrogen gas. So here we can say that this guy over here is a better oxidizing agent. Remember, the standard reduction potential tells you how readily something accepts electrons, how readily it undergoes reduction, and that means how good an oxidizing agent it is. If it's more positive, this is more positive than 0, this is more positive, therefore this guy is better at gaining electrons, it's a better oxidizing agent. So this is going to be your oxidizing agent, right? It's going to gain electrons, undergo reduction, and then here hydrogen will therefore lose electrons, right? So we're going to have the backward reaction here. Hydrogen is going to lose electrons. So electrons will flow from the standard hydrogen electrode. Electron will flow from the standard hydrogen electrode to the other half cell. Okay, so our movement of electrons will be from the right to the left. In the diagram I've drawn, that means we know that electrons flow from negative to positive. So this is a negative, and then this is the positive terminal. Table 3.1 lists relevant electrode potential for some electrode reactions for use in D part 1 and D part 2. Ethanol is oxidized to ethanoic acid in the presence of dichromate 6 ions. Construct the ionic equation for the oxidation of ethanol to ethanoic acid using dichromate 6 in acidic conditions. Calculate the cell potential for this reaction. So over here, we have dichromate 6 as the oxidizing agent, right? We have dichromate 6 as the oxidizing agent, so that's going to undergo reduction. So we have this half equation, right? We have this half equation over here, right? That's dichromate 6 undergoing reduction. It's the oxidizing agent. And then ethanol is going to undergo oxidation. So we have this guy, right? CH3CHO undergoing oxidation. So we're talking about the backward reaction here. Ethanol undergoes oxidation to form carboxylic acid. So we have CH3CHO, okay, the backward reaction plus H2O gives us CH3COOH plus 2H plus 2E minus. Okay, so again, that's the backward reaction here. Now we want to balance the electrons. So I'm going to multiply the lower equation by 3, right? Because we have 6 electrons here, we have 2 here. So multiply this by 3, we get 3 of this, we get 3H2O, we get 3 of this, we get 6H plus and then 6E minus. And then for the overall equation, cancel out the electrons. We have Cr2O7 2 minus plus we have 14H plus here on the left, we have 6H plus down here on the right. So net we have 8H plus on the left, so we have plus 8H plus, right? 14 here, 6 here, so we're left with 8 here, so we have 8H plus, and then we have 3CH3CHO as a reactant, so 3CH3CHO. We also have 3H2O here, but we have 7H2O here. So the net is 4H2O on the right, right? 4H2O on the right. So these are our reactants, and then we get 2Cr3 plus. We have 3 of these ethanoic acid, and we have 4H2O. Okay, we have 2Cr3 plus 3 CH3 COOH, and then we have 4 H2O. And then for the cell potential for this reaction, again, this is our cathode, right, or where the reduction is taking place, and then this is our anode, right, anode. So we're taking the reverse reaction here, right, that's where oxidation is taking place. So for the cell potential, we can just take the reduction potential at the cathode minus the reduction potential at the anode. Okay, that would be 1.33 minus 0.94. 1.33 minus 0.94. That would give us positive 2.27 volts. The next part says, in an ethanol oxygen fuel cell, ethanol and oxygen gas are in contact with two inert electrodes immersed in an acidic solution. The cell reaction for the oxidation of ethanol by oxygen is shown. Calculate the Gibbs free energy change in kilojoules per mole for the oxidation of ethanol by oxygen. Now the Gibbs free energy change is equal to minus NFE, okay, where E is the cell potential, F is Faraday's constant, and N is the number of moles of electrons. N is the number of moles of electrons. Now, if you go back to the table above, right, when we go from ethanol to ethanol, we're losing 2 electrons. Ethanol to ethanol, we're losing 2 electrons. And then to go from ethanol to ethanoic acid, you're losing 2 electrons. Ethanol to ethanol, 2 electrons. Ethanol to ethanoic acid, 2 electrons. We want to go from ethanol to ethanoic acid. Ethanol to ethanoic acid. So we're losing a total of 4 electrons, and then oxygen is gaining 4 electrons. So ethanol, 2 electrons lost ethanol, 2 electrons lost ethanoic acid. So 4 electrons lost, and oxygen gains 4 electrons. The number of moles of electrons being exchanged, is 4. Faraday's constant is 96,500, and the cell potential is 2.01. And this gives us the standard Gibbs free energy change as negative 775,860 joules per mole. Okay, joules per mole. Okay, again, in this expression, we're using SI units. Okay, we're using SI units for Faraday's constant, the cell potential, as well as the number of moles. So we want to convert this to kilojoules. So we divide this by 1,000. Okay, and the answer is negative 776 kilojoules per mole to 3 significant figures. So here we have question number 4, which says the 3D orbitals in an isolated Fe2 plus ion are degenerate. Degenerate means they're at the same energy. Complete the diagram to show the splitting of the 3D orbital energy levels in an isolated Fe2 plus ion and when Fe2 plus forms an octahedral complex. In an octahedral complex, they are non-degenerate. Okay, they're split into 2 different sets. So in an isolated Fe2 plus ion, right, in an isolated Fe2 plus ions, your 5 d orbitals are at the same energy. So 1, 2, 3, 4, and then 5. And then when this guy forms an octahedral complex, right, these orbitals are repelled to a higher energy. Okay, but the 2 orbitals along the axes are repelled more. Okay, the 2 along the axes are repelled more, whereas the 3 between the axes are not repelled as much. Okay, the 3 between the axes are not repelled as much. So we get this 3-2 splitting pattern. Okay, we get these 3-2 splitting pattern, right? Again, all 5 are repelled to a higher energy, but these 2 are repelled more than these 3. Okay, so we get a 3-2 splitting pattern. Bipyridine is a bidentate ligand. Explain what is meant by a bidentate ligand. A bidentate ligand is a species that donates two lone pairs of electrons, to form two coordinate bonds or dative covalent bonds to a central metal atom or ion, okay, to a central metal atom or ion. The complex Fe pyrimidine 3 2 plus exists as two stereoisomers. Complete the three-dimensional diagrams show the two stereoisomers of this complex. State the type of stereoisomerism shown. Use this to represent this ligand in your diagrams. So if we have three bidentate ligands in an octahedral complex, the type of isomerism is optical isomerism. Okay, it's optical isomerism. So we have this, this, this. Okay, we have an octahedral complex, octahedral here, this, and then this, right? And then we have to show the three bidentate ligands, right? So we have one, we have two, and then we have three. Okay, like this. Now again, in the mirror image, right, in the optical isomer, whatever is shown on the right will be shown on the left. So we have N and N like this, we have N and N like this, and then whatever is shown on the left will be shown on the right. So this and then this. And the type of isomerism is optical isomerism. Standard electrode potentials can be used to compare the stability of different complex ions for a given transition element. Table 4.1 lists electrode potential for some electrode reactions for the Fe3 plus Fe2 plus systems. Use relevant data from table 4.1 to state which iron 3 complex is hardest to reduce. Explain your answer. Reduction is the gain of electrons. So when we say hardest to reduce, we mean that it least readily gains electrons. If it least readily gains electrons, that means that's the guy with the lowest reduction potential. The lowest reduction potential here is for this particular complex, right? It's for this particular complex. So the complex is FeCN6 3 minus, and the reason why is because it has the lowest reduction potential, right? So lowest E naught. Okay. This just means that this guy does not readily accept electrons, so that means that this equilibrium is furthest to the left, right? This equilibrium is furthest to the left. Okay, equilibrium is furthest to the left, right? The more the complex ion accepts electrons, right, the better it is at gaining electrons, undergoing reduction, and the further the equilibrium is to the right. Accepts electrons, equilibrium will be further to the right. Okay. The ligand bipyridine consists of two pyridine rings. Pyridine C5H5N and benzene C6H6 have similar planar cyclic structures. By reference to the hybridization of the carbon atoms and the nitrogen atom, and orbital overlap suggest how the sigma and pi bonds are formed in a pyridine molecule. Now again, we have a similar thing happening here that we do with benzene, which means that the nitrogen and the carbon atoms must be sp2 hybridized, right? The nitrogen and the carbon atoms must be sp2 hybridized. So you can say the nitrogen and the carbon are sp2 hybridized, right? sp2 hybridized, okay? And then we have a similar thing happening here, right? That we do with benzene. So these hybrid orbitals, right? These hybrid orbitals form sigma bonds, right? These hybrid orbitals are involved in sigma bonding, okay? Hybrid orbitals form sigma bonds, right? By head-on overlap, okay? By head-on overlap, we have to refer to how the overlap between the orbitals results in the formation of sigma and pi bonds, okay? By head-on overlap. And then over here we have a delocalized, okay? Delocalized pi bond, right? Forms as a result of sideways overlap, right? Sideways overlap. of p orbitals. Okay, sideways overlap of p orbitals. These are the unhybridized p orbitals. Okay, these are the unhybridized p orbitals. Pyridine reacts with chlorine in the presence of AlCl3 as shown in figure 4.3. The mechanism for this reaction is similar to that of the chlorination of benzene. AlCl3 reacts with chlorine to generate an electrophile Cl+, and then that Cl+ electrophile reacts with this compound. We have to complete the diagram to show the mechanism for the reaction of pyridine with Cl+. So the first thing we're going to do is show a curly arrow from the ring, okay, from the ring, curly arrow from the ring to the Cl+. Okay, we end up with this sort of an intermediate, right? So we have this over here, N, and then we have this, we have this, we have this, right? We end up with a chlorine over here, okay, and an H, okay, not the carbon bonded to the nitrogen but the one next to it, right? We're going to show the ring open up. I'm going to show the ring open up towards that carbon, right, where the chlorine is bonded, like this, okay, and then I'm going to show a curly arrow from the bond, and then back into the ring like this, from the CH bond back into the ring, and we end up making our final product. Okay, we end up making our final product like this, and we have a chlorine here, and we have H+. So here we have question number 5, which says compare the relative acidities of benzoic acid, phenylmethanol, and phenol. Explain your reasoning. Now we know that carboxylic acids are stronger acids than phenol, right? They're both weakly acidic. Carboxylic acids are weak acids, phenols are even weaker acids, and then obviously alcohols are obviously not acidic, right? They don't form acidic solutions. The most acidic here would be benzoic acid, okay, benzoic acid, followed by phenol, followed by phenylmethanol, okay, phenylmethanol. And remember, the acidity is explained by the stability of the conjugate base. Okay, acidity is explained by the stability of the conjugate base. Carboxylic acids, right, when they lose their proton, they make this conjugate base, right? Their conjugate base has this COO minus, right, the carboxylate ion. And in this guy, the negative charge is delocalized. The negative charge is delocalized over the two oxygen atoms. The negative charge is delocalized or spread out over the two oxygen atoms, which means that this guy is a relatively weak base because the negative charge is not very strong. Okay, it's more delocalized, so the charge density is lower here, right? Which means that this guy does not accept protons as easily. Weaker conjugate base, or more stable conjugate base means a stronger acid. So we're going to say in the benzoate ion, that's the conjugate base, right? The benzoate ion, right? The negative charge is delocalized, okay, is delocalized over the two oxygen atoms, okay, over the two oxygen atoms, okay, making it the most stable conjugate base, okay, making it the most stable conjugate base, okay, followed by the phenoxide ion, right? Now in the phenoxide ion, right, in phenol we have this benzene ring, right? When the phenoxide ion, again the benzene loses the H bonded to the oxygen. Now this negative charge is delocalized or spread over the benzene ring, right? It's delocalized into the benzene ring. So this lone pair delocalizes into the benzene ring. The lone pair delocalizes into the pi electron system, right? So there is delocalization of this negative charge as well. Not to the same extent, but there is still delocalization here, okay? But in the case of alcohol, there's no delocalization as such. So we can say that this conjugate base is the second most stable, right? So followed by the phenoxide ion, right? That's the conjugate base for phenol, where the lone pair, okay, the lone pair of electrons on the oxygen atom, okay, on the oxygen atom delocalizes into the ring, right? Delocalizes into the ring, making it more stable, than the phenyl methoxide ion, okay, the phenyl methoxide ion. That would be the conjugate base of phenyl methanol, okay. So again, the more stable the conjugate base, the stronger the acid. A series of 9 separate experiments is carried out as shown in table 5.1. Complete the table by placing a tick in the relevant box if a reaction occurs. Place a cross in the box if no reaction occurs. Now, sodium metal will react with any compound that has an OH group, so it will react with all three. Sodium hydroxide will only react with benzoic acid and phenol, right? Because those guys form acidic solutions. They will not react with alcohols. And then sodium carbonate will only react with the carboxylic acid. Sodium carbonate will only react with the carboxylic acid because phenol is not a strong enough acid to react with sodium carbonate, okay? Phenol is not a strong enough acid to react with sodium carbonate. It reacts with sodium hydroxide but not sodium carbonate. Benzoyl chloride C6H5COCl can be synthesized by the reaction of benzoic acid with either PCl5 or SOCl2. Complete the equations for these reactions. So carboxylic acid, when they react with PCl5, you get an acyl chloride, you get POCl3, and you get HCl. Okay. The observation is you're going to see white fumes of HCl. If a carboxylic acid reacted with SOCl2, again you get acyl chloride, but you get SO2 and HCl as well. Use your answer to C part 1 to suggest why it is easier to isolate in a pure form the acyl chloride from reaction 2 compared to reaction 1. The reason it's easier to isolate, in other words, obtain, okay, the reason it's easier to isolate or obtain the acyl chloride from here is because you have two gases being produced, right? SO2 and HCl are both gases, right? So they'll easily be given off, so you're only going to be left with your product, okay? So here we can say SO2 and HCl, right, which are the byproducts of reaction 2, right? Byproducts of reaction 2 are both gases, right? Are both gases, and therefore they can easily escape. Benzoyl chloride is hydrolyzed by water at room temperature to form benzoic acid. Complete the diagram to show the mechanism for the reaction between the acyl chloride, benzoyl chloride, and H2O. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. The mechanism for this is called an addition-elimination mechanism. Okay, addition-elimination. So over here we show the partial positive on the carbon, the partial negative on the oxygen. Right, we're going to show the lone pair on the oxygen here. So the first stage is we're going to show a curly arrow from the lone pair on the oxygen to the delta positive carbon, and at the same time the pi bond breaks, both the electrons go to the oxygen. Okay, so the first stage is the addition stage. The first stage is the addition stage. We end up with an intermediate like this. What do we get? We get this O to the minus, we get a Cl, and we get this H2O. So in the first stage we have addition, and then the second stage we have elimination. Okay, first stage is addition, the second stage is elimination. In the elimination stage, the pi bond reforms and the chlorine leaves. Okay, we can also show the H leaving is H plus, okay, but they don't really require that. So what we end up getting here is, benzoic acid. Okay, I'm going to show the H plus leaving here as well. Again, this is not required. Okay, but these two arrows are more important. Okay, the pi bond reforming and the chlorine leaving. Okay, and the mechanism is called addition elimination. Okay, addition elimination. First stage is addition. Okay, nucleophilic addition stage, and then we have the elimination of the halogen, the chlorine. Acyl chlorides react with sodium carboxylates to form acid anhydrides as shown in figure 5.1. An anhydride is this group over here, the COOCO, COOCO, okay? And this guy forms when an acyl chloride reacts with a sodium carboxylate. That's a salt of the carboxylic acid, right? That's a salt of the carboxylic acid. So I'm going to highlight the bond that forms here. This is the bond that forms, okay? This is the bond that forms. The oxygen from the salt, right? The salt has this R prime group, right? This group over here. So this is your carboxylic acid salt, right? The oxygen over here, okay? The oxygen over here bonds to the C double bond O from the acyl chloride. The C double bond O from the acyl chloride, right? That C double bond O is bonded to this R group, okay? That C double bond O is bonded to this R group. So we're looking for this anhydride group. We're looking for this anhydride group in this polymer, right? They're saying condensation polymers, polyanhydride and polyester are formed by similar methods, okay? The repeat unit of the polyanhydride is shown. We have to use figure 5.1 and figure 5.2 to suggest the structure of the two monomers used to make this polyanhydride, okay, to make this condensation polymer. So we're first going to look for the anhydride linkage. The anhydride linkage is right here, right? We have this COOCO. So then what do we have here? We're going to have to break this anhydride linkage. Now if you were to break this anhydride linkage, okay, if you were to break this anhydride linkage over here, right, we can break it here or we can break it here. Okay, we can break it here or here. Okay, so I'm just going to break it right here. Okay, I'm going to break this anhydride linkage over here. And then I'm going to break the anhydride linkage over here. Okay, I'm going to break the anhydride linkage over here, right? So this polyanhydride is forming between a diacyl chloride and a dicarboxylate. Remember, we have a diacyl chloride and a dicarboxylate, similar to what we have with polyesters, right? With polyesters, we have diacyl chloride and a diol, right? Here we would have a diacyl chloride and a dicarboxylate ion. So I break the anhydride linkage here and I break the anhydride linkage here, right? Now we know that this oxygen comes from the carboxylate ion, right? So this group and this group used to be a carboxylate, right? These two used to be carboxylate groups, okay? This and this used to be carboxylate groups, and then this oxygen from the carboxylate group will bond to an acyl chloride, right? The C double bond O from the acyl chloride. So this C double bond O had a chlorine bonded to it, and then this C double bond O also has a chlorine bonded to it in the initial monomer. So how will we draw this? Well, over here, I'm going to draw this out, right? This guy used to be an acyl chloride, so I'm going to start with a chlorine. Okay, I'm going to start with a chlorine. Then we have a C double bond O. The C double bond O is bonded to a benzene ring, like this. That benzene ring is bonded to an O, CH2, CH2, CH2O. So we have an O, then 1, 2, and then 3 CH2s. And then we have another oxygen. And then that oxygen is bonded to a benzene ring that is then bonded to a C double bond O and then a Cl. Okay, so that oxygen is bonded to a benzene ring like this, which is bonded to a C double bond O and then a Cl. Okay, so that's one monomer. Okay, that's one of the monomers. And then the other monomer, right, we have a dicarboxylate. So we have this guy here, which is a CO and then O and A, right? And then we have a CH2, 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 so CH2, 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 and then that's bonded to a C double bond O, that's bonded to an O and A. Okay, so this dicarboxylate and this acyl chloride, diacyl chloride, okay, will combine to give us this polyanhydride. Polyanhydrides are biodegradable polymers. Suggest how this polyanhydride can be degraded. They're biodegradable because they can undergo hydrolysis, right? The reason they can be degraded is because they can be hydrolyzed, okay? They can be hydrolyzed, okay? They can be hydrolyzed using dilute acid, okay? Using dilute acid or alkali, okay? Dilute acid, or we can use an alkali to hydrolyze it, okay? So here we have question number 6, which says describe what is meant by a racemic mixture. A racemic mixture is a mixture of two enantiomers in equal amounts. Okay, a mixture of two enantiomers a mixture of equal quantities, okay, equal quantities or equal amounts of two enantiomers, quantities of two enantiomers. Asparagine is an amino acid that contains a chiral carbon atom and displays stereoisomerism. Separate samples of asparagine are dissolved in CdCl3 and analyzed using carbon-13 and proton NMR spectroscopy. Predict the number of peaks seen in the carbon-13 and proton NMR spectra of asparagine. For the carbon-13 NMR spectrum, the number of peaks is the number of non-identical carbon atoms. Here, all 4 carbon atoms are non-identical. The number of peaks will be 4. For the proton NMR spectrum, we're looking at the number of non-identical hydrogen atoms. Non-identical hydrogen atoms. We have 1, we have 2, we have 3, 4, and then 5. So we have 5 non-identical hydrogen atoms, so we would see 5 peaks. The isoelectric point of asparagine is at pH 5.4. Describe the meaning of the term isoelectric point. The isoelectric point is the pH at which, an amino acid, has no net charge, has no overall charge, or no net charge, electric charge, no overall electric charge, or we can say electrically neutral, it's electrically neutral. Draw the structure of asparagine at pH 1.0. So we're going to take asparagine right here, right? This is asparagine. Okay, and we know that the isoelectric point, of asparagine is at 5.4. So here the pH is below the isoelectric point. The pH is below the isoelectric point. The pH is below the isoelectric point. That means that the amino acid is positively charged. Okay, the amino acid is positively charged, right? Because at the isoelectric point is neutral. At a lower pH, we have more H plus ions. When we have more H plus ions, what happens is that this NH2 will gain a proton. Okay, it will gain a proton and make NH3 plus. Okay, so what do we have here? This would be the structure of the amino acid at pH 1. Okay, this would be the structure of the amino acid at pH 1. It would have a positive charge. Asparagine can polymerize to form polyasparagine. Draw the structure of polyasparagine showing 2 repeat units. The peptide linkage should be shown displayed. Okay, so we're first going to take this asparagine again. Now over here, of course, we're going to get a polyamide, right? We're going to get a polyamide because we have an amino acid. An amino acid has an amine group. It has an amine group and it has this carboxyl group, right? So these are the groups that are going to be reacting, right? These are the groups that are going to be reacting to form the polyamide. Okay. Note that this is already an amide group. This will not be involved in the polymerization. The amide will not be involved in the polymerization, right? We have a CON. So this is not going to be involved in the polymerization. It's going to be these two. So what I'm going to do is I'm going to draw it like this, okay? I'm going to show the amino acid like this, okay? I have a C with a COOH, right, like this, COOH like this, right? Then the C has a hydrogen, okay? The C has a hydrogen, okay? The C is also bonded to a CH2CONH2. It's bonded to this carbon is bonded to a CH2CONH2. Again, that's not involved in the polymerization, so I want to show it here. We have a CH2CONH2, and then this guy is bonded to an NH2. So we have an NH2 like this. Okay. Now, what happens is that the nitrogen from the amine bonds to the C double bond O from the carboxyl group. The nitrogen from the amine bonds to the C double bond O from the carboxyl group. Okay, so the carboxyl group will end up losing the OH, right? And the amine will end up losing the H, like this, right? So this is one repeat unit. Again, the C double bond O will bond to the nitrogen from the amine. So it will bond to the nitrogen from the amine. We have an NH, and then we have a CH, we have a CH2, CONH2, and then we have a C double bond O, and then the continuation bond, right? Again, the carboxyl group will lose the. This is a section of the polymer showing 2 repeat units. This is a section of the polymer showing 2 repeat units, okay? Section of the polymer showing 2 repeat units. The isoelectric point of lysine is at pH 9.8. A mixture of the dipeptide lysine asparagine and its two constituent amino acids asparagine and lysine is analyzed by electrophoresis using a buffer at pH 5. The results obtained are shown in figure 6.3. So they've shown us the results of the electrophoresis experiment right here. We need to find the identities for the species responsible for spots E, F, and G and explain our answer. Now they've told us that the pH for this electrophoresis experiment is 5. Okay, so the pH is 5.0, right? Lysine has an isoelectric point of 9.8, right? Lysine has an isoelectric point of 9.8. That is given to us, right? Isoelectric point of 9.8 for lysine. And then the isoelectric point for asparagine was given to us as 5.4. Okay. So the pH of the buffer is below the isoelectric point. The pH of the buffer is below the isoelectric point, means that lysine would have a positive charge. Lysine would have a positive charge. Similarly, asparagine, right, had an isoelectric point of 5.4. The pH is below the isoelectric point. The pH is below the isoelectric point. So again, this would be positively charged. And then the dipeptide, okay, dipeptide, you don't really need to know how to find the isoelectric point. The idea is that the isoelectric point would be somewhere in between. Okay, the isoelectric point would be somewhere in between, right? So here, the isoelectric point would be somewhere in between. So let's just take the average of 5.4 and 9.8. That would be 7.6. Okay, roughly. So again, that means that the pH is below the isoelectric point, so it has a positive charge. So now we have to identify the spots E, F, and G. Now over here, one thing to note is that obviously they're all positive, so they're all going to move towards the negative, right? They're all going to move towards the cathode. However, the thing to keep in mind is that in the case of asparagine, right, the pH is very close to the isoelectric point. The pH is very close to the isoelectric point. The pH is 5 and the isoelectric point is 5.4. So what we can say is that they're approximately equal. Okay, they're approximately equal in this case, which means that the positive charge, okay, overall, the average charge on all the amino acids for asparagine will not be very positive. A lot of the amino acids will remain neutral. Okay. So we don't have a very strong positive charge, okay, in the entire sample of asparagine. Okay, so over here, asparagine will actually move the shortest distance. Okay, asparagine will actually move the shortest distance because the isoelectric point is only slightly above the pH. Okay, there's not a big difference between the isoelectric point and the pH. That means that only some of the amino acids will have a positive charge. So the overall positive charge in the sample will not be very positive. Okay, the average charge on the amino acid. Now the greatest distance will be moved by lysine. The greatest distance will be moved by lysine. Why? Because it's much lighter than the dipeptide. Okay, it's much lighter than the dipeptide. So G would be lysine, right? And then obviously the dipeptide is much heavier, so it's going to move a shorter distance. Okay, so here in the middle we have lysine, asparagine. Okay, so the explanation here is that asparagine has a very slight positive charge. Okay, very slight positive charge. Only some of the molecules have a positive charge, right? So the average charge on each molecule is slightly positive, so slight positive charge. Therefore, it moves the shortest distance. Okay, moves the shortest distance, and then we would say that lysine moves a greater distance. Okay, moves a greater distance than the dipeptide. Okay, than the dipeptide because it has a lower MR. because it has a lower MR. Thin layer and gas liquid chromatography can be used to analyze mixtures of substances. Each type of chromatography makes use of a stationary phase and a mobile phase. Complete table 6.1 with an example of each of these. So in thin layer chromatography, the stationary phase can be made of silicon dioxide or silica or aluminum oxide. Okay, so silica or aluminum oxide. So here I'll just go with silica. Okay, that's a more common choice. Then for gas liquid chromatography, the mobile phase has to be an inert gas. Okay, it has to be an inert gas. Okay. So an example would be something like nitrogen gas or something like neon. Okay, these are inert gases, or helium. Okay, these are examples of inert gases that you can use. An unknown amino acid is analyzed using thin layer chromatography. 2 chromatographs of the unknown amino acid and 4 reference amino acid P, Q, R, and S are obtained using 2 different solvents. Identify the unknown amino acid. Justify your answer. Now, if you look at both the chromatographs, right? The unknown amino acid in solvent 1, when we're using solvent 1, matches Q and S. Okay, it matches Q and S. But with solvent 2, the unknown amino acid is only matching with R and S, okay, instead of Q and S. So the unknown amino acid matches with S, it matches with S in both solvents. Okay, it matches with S in both solvents. So that means that the unknown amino acid must be amino acid S. Okay, it must be amino acid S, and the reason why is because it has the same RF value. It has the same RF value as S in both solvents, right? In both solvents or in both chromatographs. A mixture containing 3 organic compounds is analyzed by gas chromatography and mass spectrometry. The gas chromatogram is shown. The area underneath each peak is proportional to the mass of the respective compound in the mixture. The concentration of K in the mixture is 5.52 into 10 to the power minus 2 grams per decimeter cube. Calculate the concentration in moles per decimeter cube of compound L. Now again, the question is saying that the area under the graph is proportional to the mass of each compound present, right? It's proportional to the mass of each compound present. Okay, so we're going to do all our calculations in per dm cube here. Okay, we're going to do all our calculations in per dm cube over here. Okay, now if you think about per dm cube, right, per decimeter cube, right, we can say that K has a mass of 0.0552 grams, 0.0552 grams, and the area of K is 44. The area of K is 44. So this area here corresponds to a mass of 0.0552 grams. Okay, corresponds to a mass of 0.0552 grams. The area for L is 58. The area for L is 58. Okay, 58. So we can find the mass of L present per decimeter cube, right? If we just cross multiply here, we get the mass of L, as 0.0728 grams. And again, this is the mass per decimeter cube. I want to convert that to moles per decimeter cube. So to find the moles, we can just take the mass and divide by the molar mass. So that would be 0.0728 divided by 116. Okay, that's given to us. That's the MR of L. And here we get 6.27 into 10 to the power of minus 4. 6.27 into 10 to the power of minus 4 moles per decimeter cube. So 6.27 into 10 to the power of minus 4. So here we have question number 7, which says procaine is used as an anesthetic in medicine. It can be synthesized from methylbenzene in 5 steps as shown in figure 7.1. Name all the functional groups present in procaine. So procaine is this final product here. What do we have? Here we have a tertiary amine. we have a tertiary amine, right? We have a nitrogen bonded to 3 carbons. So we have a tertiary amine or tertiary amine. We have an ester linkage, right? We have a COOC. So we have an ester linkage, right? We have a phenylamine group, right? We have a phenylamine group over here, right? Because we have an NH2 bonded to the benzene ring. So we have a phenylamine group. Okay, so these are the functional groups present in procane. A molecule of procane has 13 carbon atoms. State the number of carbon atoms that are sp, sp2 and sp3 hybridized in procane. Now the sp2 carbon atoms are the ones that are making single bonds, right? That are making single bonds, only single bonds. So we have this CH2, CH3, right? That's 2 carbons here. That's 2 carbons here, but we have 2 of these ethyl groups. We have 2 of these ethyl groups. So that would be 2 times 2, that's 4 carbons. And then we have these 2 carbons as well, right? We have these 2 carbons as well. So that's 6 carbon atoms that are sp3 hybridized. Okay. Now the sp2 carbons are the ones that are making double bonds, the C double bond OO, right? The carbons that are bonded to 3 atoms, the carbons that are bonded to 3 atoms, so that's this one. And then obviously we have the 6 carbons on the benzene ring, right? So we have 6 on the benzene ring plus 1 from the ester, so that's 7 sp2 carbons, and then we have 0 sp carbons. Okay, we have 0 sp carbons. The proton NMR spectrum of procane dissolved in D2O is recorded. Predict the number of peaks observed. Now in D2O, right, the NH and OH peaks disappear. Okay, the NH and OH peaks disappear, right? Because these are what we call labile protons. Labile protons are hydrogen atoms bonded to nitrogen or oxygen, right? Highly electronegative atoms. So in the proton NMR spectrum, we're not going to see this proton, right? We're not going to see the peak for this particular proton. What we are going to see is we're going to see peaks for these 2 protons, right? So I'm going to label these. I'm going to label these as HA, right? This is HA. We're going to see peaks for these 2, right? These 2 are identical. That's HB, right? We're going to see peaks for this guy and then this guy. So this is HC. We have HC here. We have HD, right? This is the 4th type. And then we have this CH2, right? Both of the ethyl groups are identical. Both the ethyl groups are identical, but obviously the CH2 protons are different from the CH3 protons. So this is HE. And then lastly, here we have HF. Okay. So we're going to see 6 peaks in the proton NMR spectrum, right? Theoretically speaking, we would see 6 peaks. Now, practically speaking, of course, these 2 different peaks on the benzene rings will show up as one peak, right? Will show up as one peak, but theoretically they are 2 different protons. So here we're going to see 6 different. We're going to see peaks for 6 different protons. Okay, theoretically speaking, we're not going to see the peak for this NH2 proton. State why procane can act as a base. The reason it can act as a base is because it has the amine groups, right? The nitrogen here as well as the nitrogen here. So both of these nitrogen atoms are amine groups, right? They're amines and they can accept a proton, right? So over here we can say that the nitrogen atom in the amine, right? In the amine groups or the amine groups can accept a proton, right? They donate a lone pair of electrons, right? They can donate a lone pair of electrons and accept a proton. Compound X can be synthesized in 2 steps from methylbenzene. Now over here we're doing 2 things, right? What we're doing is we're converting the methylbenzene group to a carboxyl group, and we're also substituting a nitro group onto the benzene ring. Now over here we wouldn't make, okay, we wouldn't make the carboxyl group first, okay? We won't oxidize the methylbenzene to a carboxyl group first. Okay, we won't do this first. The reason why we won't do this is because the carboxyl group is 3 directing. The carboxyl group is 3 directing, which would mean that if we oxidize a methyl to a carboxyl group, right, then the nitro group will go on carbon number 3. It will go here or here. We don't want that, right? We want the nitro to go on carbon number 4. So the first thing we're going to do here is the nitration of this methylbenzene. Okay, nitration of methylbenzene, because the methyl group is 2,4 directing. The methyl group is 2,4 directing. We're first going to get an NO2 group. We're going to get an NO2 group over here, and then we're going to oxidize the methyl group to a carboxyl group. Okay, so the reagents and conditions for step 1. In step 1, we're converting methyl benzene to this 1-methyl 4-nitrobenzene, right? 1-methyl 4-nitrobenzene. So here in step 1, we're going to use concentrated nitric acid, right? Concentrated nitric acid and concentrated sulfuric acid, right? That's the nitration of benzene, right? At a temperature of 50 degrees Celsius. At 50 degrees Celsius, okay? That's a suitable temperature for this reaction. And then in the second step, we're going to convert this methyl group into a carboxyl group. So that's the oxidation of alkyl benzene. We're going to use hot alkaline KMnO4 followed by H plus. Okay, followed by H plus. Procane is synthesized in 3 steps from X. Suggest the reagents and conditions for step 4 and for step 5 in figure 7.1. We go back to the figure over here, right? In step 4, what we're doing is we're converting this acyl chloride, okay, we're converting this acyl chloride into an ester, right? So this acyl chloride must be reacting with an alcohol, okay? This acyl chloride must be reacting with an alcohol. So we have this guy, right? We have this entire guy over here, right? And this oxygen must have been bonded to a hydrogen, right? This oxygen must have been bonded to a hydrogen. So what do we have? We have a nitrogen with 2 ethyl groups and then a CH2OH, okay? And then in step 5, what we're doing is we're reducing the nitrobenzene to a phenylamine, right? We're reducing the nitrobenzene to a phenylamine. For that, we're going to use tin and concentrated HCl, okay, and heat. We're going to use tin as the reducing agent and concentrate HCl and heat, okay? So here we have this alcohol, right? This is going to be a CH2OH. So we have a nitrogen with 2 ethyl groups and then a CH2OH. Okay, so for step 4, we're going to use this guy over here. We have a CH3, CH2 twice bonded to a nitrogen, which is bonded to a CH2, and then OH. This alcohol reacts with acyl chloride to form ester. And then for step 5, we're going to use tin and concentrated HCl and heat. Explain what is meant by partition coefficient. Partition coefficient is the ratio of the concentration, okay, the ratio of the concentrations of a solute in 2 immiscible solvents, okay, in 2 immiscible solvents at equilibrium, in 2 immiscible solvents at equilibrium. Okay, and this has to be at a constant temperature, obviously, right? It's determined at a constant temperature. If you change the temperature, the partition coefficient will change. The partition coefficient of procane between octane 1-ol and water is 1.77. Octane 1-ol and water are immiscible. A solution containing 0.5 grams of procane in 75 cm3 of water is shaken with 50 cm3 of octane 1-ol. Calculate the mass of procane that is extracted into the octane 1-ol. So again, the Kpc is the ratio of the concentration, the partition coefficient. Kpc is the ratio of the concentration of procane. Okay, I'm going to call procane X over here. The ratio of, so we have concentration of procane in the organic solvent divided by the concentration of procane in water, okay, or in aqueous solution. And this partition coefficient is given to us as 1.77. Okay, it's given to us as 1.77. Now the initial mass of procane is 0.5 grams. Okay, the initial mass of procane is 0.5 grams. Okay, now we're gonna say over here that after the extraction, right, let's say that y grams is extracted. Okay, y grams is extracted. So after the extraction, right, in the organic layer, right, we said we're gonna say that y grams were extracted. Okay, y grams are extracted, and the volume of the organic layer is 50 centimeter cube, right? The volume is 50 centimeter cube. And then obviously initially we had 0.5, we extracted y grams, so that means in water we have 0.5 minus y grams, 0.5 minus y grams, right, left. And the volume over here is 75 centimeter cube, right, 75 centimeter cube. Now, for the concentrations, we can just use the units grams per centimeter cube, okay? Doesn't matter what units you use as long as they're the same in the numerator and the denominator, because the partition coefficient is unitless. So here we're going to say the concentration in the organic solvent is the mass in the organic solvent, which is y grams, divided by the volume, so y over 50, divided by concentration in water, which is 0.5 minus y divided by 75. So 0.5 minus y divided by 75. And this is equal to 1.77, right? This is equal to 1.77. So now we're going to find the value of y. Okay, we're going to find the value of y. So here, okay, what we get is this, right? If I rearrange this expression, I get 1.77 times 0.5 minus y over 75 is equal to y over 50. Okay, and if you solve for y, over here, you're going to get y as 0.271 grams. Okay, 0.271 grams. So the answer here is 0.271, right? That's the mass of propane extracted into the organic solvent, right? That's octan 1 ol.